All right, AP, let's begin chapter 17, which is, I like to call part 2 of acids and bases. It's a shorter chapter, but when we get to 17.3, that's going to be the meat of it, okay? And I want to give a shout out to David and Adamari for volunteering to record their AP Chem recruiting responses of why they love AP Chem so much and why they took it, and to help build the program year after year. So I thank you, David and Adamari. Shout out. Whoop, whoop. All right, here we go. Here we go. Common ion effect. This is big. Okay. We already know that acids dissociate. Okay. Now, if it's a weak acid, we know it partially dissociates. We'll get our hydrogen. We'll get our anion. But remember, we still got the majority of the acid didn't dissociate. So the majority of the weak acid doesn't dissociate. And we saw this when we looked at the Ka value. Okay, so when you have a Ka and we look at that exponent, that negative whatever it is, the more negative it is, the more it doesn't dissociate. Okay, so if you had somebody like -2, 3, they dissociate quite a bit. But for like a negative 5, 6, 7, 14, whatever it may be, they barely dissociate. Okay, so the point of a common ion effect is that if you have a common ion, that's why it's called common ion effect, is decreased by the addition of a strong electrolyte. Well, let's keep breaking down this definition even more. Okay, a strong electrolyte was any strong base, any strong acid, and any ionic compound. And it's going to be mostly this one that we're going to be doing, this ionic compound, that has a common ion with that weak electrolyte. Okay, so the dissociation of a weak electrolyte, aka, and the weak electrolyte we're going to be looking at is weak acids and weak bases. That's the only two we're going to be looking at. So is decreased, which means right here even less dissociation. I mean, that barely dissociates as it is, now it's going to dissociate even less. Okay, by the addition of a strong electrolyte that has a common ion with that weak electrolyte. All right, so with the weak electrolyte, we're talking about that weak acid or weak base. Okay, so when you put this definition together, the dissociation of a weak acid or base will dissociate even less if you add a strong electrolyte, aka any of those three, that has a common ion with that weak acid or base. Okay, and this is a very, very important effect that happens when we want to slow down dissociation. We would add this common ion. Okay, now let's take an example. Let's consider acetic acid, very weak acid. Okay, double arrow weak acid. Let's say we add an ionic compound that has a common ion with acetic acid. Okay, but it has to be a strong electrolyte. Okay, so that ionic compound, it's got to be a strong electrolyte. So sorry. Apparently I want to see the weather today. All right, ionic compound with a strong electrolyte with that acetic acid. So why not sodium acetate? Okay, sodium acetate, that's an ionic compound, and ionic compounds are strong electrolytes. So if I have an ion, and the ion that I have in common is right there, okay, and additional acetate ions, what's going to happen is it's going to affect him, okay, because that ion is going to dissociate. And remember, strong electrolytes, 100% dissociate. So when he hits water, he's not only going to break up into sodium, and I don't see sodium anywhere in that. okay? And then it's going to break up into my acetate ion. I'm not affecting that acid, I'm affecting the ion, okay? And what's going to happen is, very important here, equilibrium is going to shift. Now, was there a topic back in the day, aka chapter 15, where if we added a stress, aka a stress, it shifts equilibrium, called Le Chatelier's principle, okay? So it's always coming back to chapter 15, Le Chatelier, on how we affect that equilibrium, okay? So what happens is, if we add more acetate ions, aka from that sodium acetate, I am making my teeter-totter look like this. So how am I going to re-establish equilibrium? I got to shift my reaction, I got to shift it to the left. So I'm going to have to produce more acid and less hydrogen and less ion, okay? So we produced more products, but we're going to have to shift it to the left to reestablish equilibrium. So what happens is, this causes a reduction of H ions, because remember, I'm going to be losing some H and some acetate when I shift, okay? And by shifting that, a decrease in percent ionization will occur, because I'm going to produce less of these, but now I'm going to have more acid. And that more acid is going to make me dissociate even less, okay? So remember this equation, percent ionization. Why is this part important? Is because when you do percent ionization for an acid, we take that H concentration, that equilibrium, over that acid. So why will it decrease percent dissociation? Because I'm affecting him. By me shifting to the left, this number right here is going to be less, okay? Not more, it's going to be less, because I'm shifting to produce more acid. So by adding sodium acetate, we have disturbed the acetic acid equilibrium, okay? And by doing that, we have added a product of that equilibrium. We've added more the acetate ion. And this is what's called common ion effect. The extent of the ionization of that weak acid, that weak electrolyte, is decreased by adding to solution a strong electrolyte that has an ion in common with that weak electrolyte. So the whole point is that with this acid, it's going to dissociate even less, okay, by us adding this common ion. Now, I can't just add any salt that I want. I have to have a salt that's only in, that's only in common with that anion. So I couldn't add like sodium chloride. I don't have any sodium in here, and I don't have any chlorine. Let's see, I could have added maybe like potassium acetate. I could have maybe added some magnesium acetate. Yeah, doesn't matter. I don't care if there's a subscript, balanced charges, it doesn't matter. I can add any of these because they have a common ion with that acetate, okay? So you're going to see a lot of practice with this, okay? Now, 17.2 buffers. I'm not going to lie to you. It's one of those topics that's kind of like that headache topic, but it's so important because get ready to see how many learning targets there is, okay? So let's break this down. When a strong acid and strong base are mixed, they react quantitatively, quant as in numbers, in a reaction produced by the equation H and OH make water, okay? Single arrow because strong acid, strong base. So this right here came from the strong acid, that came from the strong base. The pH of the resulting solution may be determined from the concentration of that excess reagent, okay? And we know how to do pH by now. pH is negative log of that H concentration. When a weak acid and a strong base are mixed, they react quantitatively in a reaction produced by the following. Now remember right here, if this is my weak acid, I can't touch this. So you're going to get a ton of review from chapter 4, net ionic. So with weak acids, okay, you cannot break, okay? So no dissociate in that net ionic equation. So right here, this is called a net ionic. That right there came from my strong base. I got rid of the metal. I don't care about the metal. And then I have my anion, which is my conjugate base. And then I have my water, okay, conjugate acid. If the weak acid is in excess, then the buffer solution is formed, and a pH can be determined from the Henderson-Hasselbalch equation. Now, this word is going to be really important with that equation, and you're going to see him pop up later. Okay, it's coming. As long as you have a buffer, you can use this equation. And trust me, you're going to love this equation. Okay? If the strong base is in excess, then the pH can be determined from the moles of excess hydroxide and the total volume of the solution. So if they're equal, so then you'll have a slightly basic pH because of that strong base. Remember, we just did this in chapter 16. When you have somebody that came from a weak acid, a salt, and strong base, that strong base is dominating. So my pH better be greater than 7. Slightly basic, so the pH can be determined from that equilibrium, and basically we'd be using ice charts. Okay, so right here, if this is my acid, okay, and that was my base, then I would get my, or actually I wrote that backwards, okay, because this right here, HA, that is your acid. So when it donates it, I'll start with my base. So there's my base, and my acid, and my conjugate. That's how I know this cannot be acid, because OH is not acid. There's my conjugate base. Okay, there's a lot of stuff in here. So if your weak acid is in excess, you can use our Henderson-Hasselbalch equation. If the strong base is in excess, then we can determine pH from that OH excess, but we'd have to go OH concentration, we'd have to go to POH, and then we'd have to go to pH. Okay, so we got some stuff to do there. I'm just telling you all the rules first before we do examples. And if they're equal, okay, well then that's when we can use ice charts. When a weak base and a strong acid are mixed, then we'll get the following equation. So there's my base, and there's my acid. We already know hydronium, strongest ion concentration. And then I'll get my HB, so my conjugate acid, and then I would get my conjugate base. If the weak base is in excess, I have a buffer solution, and you're seeing the trend here, then I can use my Henderson-Hasselbalch equation. However, if the acid is in excess, then we can find pH by using the excess hydronium, okay? And if they're equal, then they're equal, okay? Like I said, that's when ice usually comes in. And I know I'm just giving you all the trends, ladies and gentlemen. It's not going to make sense till we actually apply it, okay? But unfortunately, AP has a lot of rules when it comes to buffers and common ions. So we got to go through every learning target that they want us to do. When a weak acid and weak base are mixed, they will react in equilibrium, and you'd see the following. So notice right there, our weak acid and weak base, then you'd get the following, okay? Notice up here, you have single arrow, but then right here, if they're equal, slightly basic, then you'd get double arrows, okay? So you're going to see like some single arrows and double arrows. You cannot use ice unless you're at equilibrium, okay? If you're not at equilibrium, then you don't use ice, okay? A buffer solution contains, now you've heard this word buffer. Why is it important? A buffer solution contains a large concentration of both conjugate acid-base pairs. The conjugate acid reacts with the added base, and the conjugate base reacts with the added acid. These reactions are responsible for the ability of a buffer to stabilize pH. So you're going to see in just a second this whole point of a buffer, okay? It's about resisting the change to pH. With I have a buffer, it's a chemical that's added, and when I add it in there, it's not going to change the pH hardly any, okay? And this is very important because when we just talked about chapter 16 salts, if we added a salt in it, it could change pH. It could be more acidic, it could be more basic. But if I have a buffer, that chemical added can resist the change. Okay, so basically, I don't want a change to happen. It may be slight, but I don't want like a huge change where it went from like pH of 2 to 5. That'd be big. The pH of a buffer is related to pKa. Very important on this part. You'll see it in the videos of the acid. And the concentration ratio of the acid-base pair. The relationship is the consequence between the equilibrium expression, we're talking about Ka, with the dissociation of that weak acid. So with Ka, and using that Henderson-Hasselbalch equation, okay? And there's some equations coming as we go through this video. And I told you there's a lot of learning targets, okay? This right here is the Henderson-Hasselbalch equation, okay? And I believe it's on your equation sheet, and it's probably a little hard to see right here, and I apologize, it's AP's typing. But right here, that should say the concentration of the conjugate base over the acid. Okay, now this is to solve for the pH, and only for the pH, because there is an OH one, and I'll write it down here. But right here, this is the Henderson-Hasselbalch equation. Okay, I'm just going to call it the HH. Adding a small amount of acid or base to a buffered solution does not significantly change the ratio between these two, and thus does not significantly change pH. And that's the point of a buffer. So if you add some acid or base, as long as it says a buffered solution, it's going to not change pH dramatically. The change in pH on addition of acid or base to a buffer solution is therefore much less than that would be in the absence of the buffer. So if I did not have a buffer solution and I just added some more acid and base, oh, it's going to change pH, okay? But if you have a buffer solution, it's not going to change the pH much. Increasing the concentration of a buffer component while keeping the ratios constant keeps the pH of the buffer the same, but increases the capacity of the buffer to neutralize added acid or base. Okay? What they're saying is if you increase concentration of a buffer component, but as long as the concentrations stay constant, and they're talking about those two right there, then it's going to keep the pH of that buffer the same. But you're going to hear something in AP, these videos, they're going to talk about capacity of buffers, increasing the buffer capacity. And I believe there's an AP Daily video just on that, okay? And you'll definitely be taking notes on that. When a buffer has more conjugate acid than base, it has a greater buffer capacity for addition of added base than the acid, okay? So when a buffer has more conjugate acid, it has a greater buffer capacity for addition of added base than acid. So if you have more acid, you're going to want to have added more base to make a greater capacity. When a buffer has more conjugate base than acid, it has a greater buffer capacity if acid was added. You see the difference? So if you have more, in this case, you have more acid than base, then you're going to have a greater buffer capacity if you add some more base. Okay, it's kind of like Chatelier's principle. So in this case, if you have more base than acid, we want to add some more acid to make this buffer stronger. Okay, so this right here, this trend, this is talking about how to make the buffer capacity stronger. Okay. Now, you're probably like, okay, Rodriguez, I'm kind of getting it, but I don't even know what a buffer is. All right, well, this is why this is part right here. A buffer is when you have a common ion effect. So remember that equation, Mr. Acetic acid? Well, just this equation by itself, Okay, all I see is a weak acid that partially dissociated. But then, if I add in somebody called sodium acetate, I have now created a common ion effect where it's going to affect him. This acetate ion, I'm going to be adding more ions to this. And by doing this, I now have a buffer. So ladies and gentlemen, if you have a common ion effect, you have just created a buffer solution. Okay? But a buffer solution, what is it? You have to have a weak acid and its conjugate, or a weak base and its conjugate. Okay? So this right here, remember if we added water into this, I would have my weak acid, there's my base, and I'd have hydronium. And then right here, this would turn into my conjugate acid and my conjugate base. A buffer contains a weak acid, these are right there, and its conjugate base, right there. Okay? That's what makes a buffer. And then I have to add in an ionic compound, strong electrolyte, add in a strong electrolyte, aka ionic compound, that has an ion in common with that ion that's in the equation. And what does a buffer do? By you adding that common ion effect, it's going to create a resistance to change of pH. So maybe in the beginning, maybe that weak acid alone, maybe the pH was, I'm just spitballing here, maybe the pH was like 5. And then when you added the common ion, maybe the pH went to like 5.2. Do you see how small of a change that is? It's not a big deal. I didn't add this common ion and the pH went to 10. That's not how it works. As long as you have a common ion with it, that resistance to change in pH, it's not going to make a big deal. And there's sometimes where scientists are trying to create an experiment where they're adding stuff to it and they don't want the pH to change much. And that's the point of it. Okay, they're trying to create maybe like a medicine or a drug that keeps the pH still maybe barely acidic. Because remember, in your body, you have mostly acidic parts, blood, organs, stomach. They don't want to give you a pill that's going to turn it basic, because that would be a really, really bad stomachache. And how does it work? Well, since a buffer contains both an acid and a base, plus its conjugate, an acid and base are present in all buffer solutions. So if a small amount of strong acid is added to the buffer, there is a base component ready and willing to neutralize this invader. Okay? So if you try to add like a strong acid to it, like HCl, you're going to have what's called a base counterpart that's going to neutralize this, so then that way it doesn't change that pH. Okay? So with this, ladies and gentlemen, you're going to go, because I'm giving you a ton of practice here with these videos. You're going to go to your, as always, I was just looking at it right here, 8.4 to 8.9 video. Okay, AP Daily, Mr. Fairbrow, he does an excellent job. He's going to give you a ton of practice. Okay, so you're going to do this example. Okay, and more examples. And more. And if I didn't say the word more enough, and more. Okay, and more. And did I mention more? This one right here is going to be very important on how to prepare that buffer solution. Okay, all right. And this is how we're going to help you with the ice charts. Okay, now this last part, before you go into your videos, okay, this is pretty much every equation that we've been using since chapter 16 and 17. Okay, right here, and I don't think the Henderson-Hasselbalch is listed up here, but it's right above. Just remember, ladies and gentlemen, this K, all of these Ks, all of them, all of them, all of them, whether it's Ka, Kb, Kc, Kp, Kw, and there's going to be one coming in this chapter called Ksp. You have to make sure temperature doesn't change. Okay, so have to. Okay. right here in this video, okay, before you go off and do your thing, okay, the Henderson-Hasselbalch equation is right here, okay. This is how we can avoid ice charts. And I know, ladies and gentlemen, we are pro at ice charts. We can do them in our sleep, but sometimes doing ice charts, they can just get to be too much, okay? So what we can do is we've got to remember that Ka, products are the reactants, okay? So I got my acid, I got my conjugates, okay? If I kind of substitute this into here and want to find pH, now this is only if I have a buffer solution. I can only use this equation, okay? I take what's called the pKa, which is the negative log of Ka, and then I take my acid concentration, this is my weak acid, and then I take that conjugate base concentration. Well, remember, that's him right there, okay? And after we practice this, you're going to be like, how does he have a number when usually in the ice chart he's 0, okay? Well, you're going to see something. You divide these and then take the log, okay? You add these two up and then you get pH. This is how we can avoid using the ice chart where we don't need to, okay? There is a pOH version when we get to bases. It's just AP doesn't ever give it to you. What you do is you take the pKb plus the log of the base now over the acid. Okay, so remember right here, this is going to be the conjugate acid. Here was the base and then conjugate base on top. I'm sorry, this was the weak acid, conjugate base on top. Down here, this is your weak base, conjugate acid on top. It's just the opposites. Okay, the Henderson-Hasselbalch equation. Teachers, for some reason, don't always like to show this equation, and I don't know why, because it's freaking awesome, because I just sometimes need a break from ice charts. Okay, if that Ka, whatever that Ka is or Kb is, if it's significantly small, usually a Ka exponent smaller than 10 to the negative 4. And what we mean by small, we're talking about those large negative ones. Okay, it's like negative 5, 6, 7, negative 12, whatever it is. Then we can use the initial values of the acid and base concentration in order to find pH. It's like doing an assumption, okay? So if that Ka value is really small, so like 10 to the negative 4, negative 5, negative 6, etc., we usually use the Henderson-Hasselbalch equation instead of doing an ice chart, okay? And you know I'm going to show you how to do that. And buffer capacity. When I teach you how to do what's called titrations, there's a region in these what's called titration graphs. This is what's called a titration graph. Okay, where you would see this buffer occur, and it's right here in this graph. Okay, buffer capacity. Okay, and like I said, you do have, I think, an AP Daily video coming on this. The amount of acid and base that can be neutralized by the buffer before there's a significant change in pH. So notice right here, if pH is on the y-axis, notice right here this pH change, if they call this the buffer region, I mean, it's like about what is that, about 4 point, maybe 5, and then right here, it's about 6. Okay, that's not a big change. But then look right here. It goes from pH 7 to about, big change here, what is that, 11? That's huge. That's a big change right here. So the buffer region is where the region is that the solution, because down here, all I'm doing is just adding base to this acid. And the pH is just going barely up, barely, just slightly. And then automatically goes shoom, goes up, big change in pH. So buffer capacity depends on concentration of the components that are in that buffer. The greater the concentrations of that conjugate acid-base pair, the greater the buffer capacity. Okay? And AP Classroom Video 8.10 is going to help you with those examples. Okay? So, you're going to go back and keep watching 8.4 videos around 41 minutes. Okay? And it's going to help you with this capacity. Okay? And you're going to see more examples. Okay? I'm trying to hit you. I've never done this before in chapter 17 with so much examples. So you guys are the first ones to get these brand new spanking notes with all these practices. Now hear me, hear me. When they show this math, ladies and gentlemen, I left you